All right, so do you guys have questions this morning? So last time we were working on those trig integrals. Before that, we had worked on integration by parts. We're going to add to the list today. We aren't going to meet on Wednesday, remember, because I'm doing virtual conference this week. So if you guys have questions, just either email me or put them up in e-learning for everyone to see, and then I will answer them in some way or another. So I might answer them in text, but I might also answer them in like a little short recording of how to do them or something like that, just when I'm not in session, and then I'll post it. So I'll either post there, a link there to YouTube, or just a video there directly. So if you do have questions on Wednesday, you can still get them answered, or even anytime in between. And of course you can do that whether it's conference or not. You can always post questions in e-learning and I'll go in and answer them. Wow, you guys are talkative today. Aaron C., how's it going? Not gonna answer me. Okay. Aaron E., how about you, other than your destroyed psyche from physics?
I'm not doing too bad.
Okay. Caitlin?
I'm doing pretty good. Pretty much just working through everything at the moment.
No
Like the
questions?
problems.
No questions arise yet?
Not yet. It's just more of like taking time to like figure out just everything really. It just takes a little bit of time. No questions right now though.
Okay. Oh, that's a good one, Aaron C. Evaluate this using the reduction formula. And so when they tell you to use a specific method, you should do that, because the form of your answer will tell them whether or not you use that method. And then they probably won't give you credit for an alternative answer that didn't use the method they describe. So it says evaluate this using reduction formulas, include plus C in your answer, and put parentheses around the argument of the trigonometric functions. So in other words, like the tangent squared x, they want a parenthesis around the x. I'm assuming those are powers. Is that right, Aaron? That's a tangent squared x. Okay. All right. So let's see if we can try that one. Did that one come up in your homework in Alta? Oh no. Okay. I will be right back. It appears that my pencil is MIA. Okay, found it. So let me escape here so I can see your question. It was this: integral tangent squared x secant to the fifth of x. So since they told us to use a reduction formula, remember those reduction formulas only have a single trig function in them. So we need to get this written in terms of a single trig function. And to do that, we're going to use the identity that said, let's see, secant squared x is tangent squared x plus 1. Or equivalently, what we're really going to use is the fact that tangent squared x is secant squared x minus 1. My sign is slow. So if we replace tangent squared with secant squared x minus 1, then everything in this integral in terms of trig functions is a secant. In fact, this is secant to the 7th of x minus secant to the 5th of x. Does that make sense so far, Aaron? And then we'll have to be careful when you go to enter that. Okay, so we're going to go grab those formulas, and we want the formula for sub that one. Oh, I thought I had it open, but I guess I don't. So we want that trig integrals handout that we had up last time. Let's see if I can go find it. So, and these formulas, obviously, I don't have them memorized, and I don't necessarily expect you to have them memorized, but you got to be able to find them. So I dug mine up. Here it is, and I've got powers of secant. And the formula looks like this. I'm going to go ahead and write down the formula, stick it in here in blue. Integral of secant of a power, and they write it as secant to the nth of x, is secant to the n minus 2 times the tangent of x, all divided by n minus 1. Then added to that is n minus 2 over n minus 1 times the integral of secant to the n minus 2 of x. And n can't equal 1. So this will work for any other power. Generally, we'll use it for powers that are larger than 0 in any case, but n can't be 1 because if it were, we'd end up dividing by 0. So there's our formula, and now we have to apply that formula to 2 different powers of secant. We have the 7th power and the 5th power. So we're going to apply the formula to both of those and then subtract and see what we come up with. Notice that there's a good chance we're going to have to use a reduction formula again on this one. Aaron, you picked a great one to get us started with. So let's see. All right, so n is 7 for the first term, and n is 5 for the second term. And we're going to work through those separately. Okay, so let's see. N minus 2 then is 5, secant to the 5th times tangent. N minus 1 is 6, plus 5/6 times the integral of secant to the n minus 2 power, secant to the 5th of x dx. So that part of this is the integral of secant to the 7th of x. Then we have to subtract the integral of secant to the 5th of x. So just let's take a quick peek, make sure you're still with me on that. So the first two terms were for the 7th power. And then the second term, the last term, is the integral of secant to the 5th of x. Are you with me, Erin, since you asked this one? Okay, so now I could complete those last two integrals separately, but notice that they involve like terms. And since they each involve using a reduction formula, I'm going to try to reduce my work as much as I can. Now I have secant to the 5th of x tangent x over 6 minus 1/6 integral secant to the 5th of x. So plus 5/6 minus 1 is minus 1/6. And then we'll just have to use that same reduction formula again, but this time for secant to the 5th of x. So now n equals 5, and we're going to repeat the formula. So secant to the 5th times tangent all over 6 minus 1/6 times a bunch of stuff. N minus 2 is 3. N minus 1 is 4. N minus 2 is 3. So 3/4 integral secant cubed x. And I think probably the hardest thing here, or the biggest source of errors, are the nested parentheses. So I actually recommend that you distribute along the way so that you don't end up with a whole bunch of nested parentheses and you have to figure out which coefficients go where. So I'm going to go ahead and distribute there. And I'm probably going to have to jump back and forth a little bit, but notice that I've got some 24ths as my coefficients. So let's see, secant to the 5th of x tangent x over 6, secant cubed of x tangent x over 24. And I'm going to go back. And then minus 3/24 integral secant cubed. So we are there. And this is a mess, but we're getting it. So secant to the 5th tangent x over 6 minus secant cubed tangent x over, x over 24 minus 1/8, and then our reduction formula again, this time with n equal to 3. So 2 less is the first power. So secant x tangent x over 3. And let's see. I might have a sign error in here. I'm going to have to just go back and double check my formula. Plus n minus 2 over n minus 1, 1/2 integral secant x dx. So I think I have most of it there. I do want to go back and peek at my first page. No, I think I'm okay. So let's see, this minus sign came from 5/6 minus 1. So that one's okay. And then the formula is a plus sign, so that's okay. And then I had 2 minus signs from distributing. So I think my signs are all good. And I think I have just one more step and I'll have this. Secant fifth x tangent x over 6 minus secant cubed x tangent x over 24 minus secant x tangent x over 24 minus 1/16, and now I just need the integral of secant x. And integral of secant x was natural log secant x plus tangent x plus c. So one thing to note on here, they said include the plus c in your answer. We have that. And put parentheses around the argument of trig function. So when you enter this in Alta, they're going to want parentheses around each of those x's. All the way through. So yeah, that's a long one. Erin, how is that? I mean, I know it's long, but notice that it's just sort of the same formula getting used over and over again. So this is kind of like a huge exercise in algebra and making sure that you don't multiply wrong, that you plug in the right numbers, and that you don't mess up signs. Okay, good, Erin. And that was a good one to ask. I think if you guys can do that one, you could probably do most any problem with the reduction formula. I mean, we do have to be careful. So for example, if a problem had secant to the 5th power of 2x, what I would probably do before using the reduction formula is just do a u substitution, let u equal 2x, and then the formula applies directly. You'll end up with a 1/2 that you have written out in front, and then you can just distribute that at the very end to make sure you have the right final answer. Let's see. Wait, in the second to last part. Oh, yes, you are right, I think, because that was, I mean, n minus 2 over n minus 1. So I think you're looking, I'm going to circle it. Are you talking about right there, Erin? Yes, because that would have been 1/2. Yes, those should match up. Thank you. So that makes that a 2, and that makes that a 16. You are correct. Thanks, Aaron. And one thing to note, I should have noticed that. Notice that in the formula in this reduction formula, these two denominators are going to match up. So that was kind of an easy error to spot. Thank you for catching me on that, Aaron. So that's really the, I'm going to go back here and I want to share from this one. Share from that evaluating trig integrals handout we had from last time. So this was the reduction formula we were using. And this actually fits on dealing with powers of tangents and secants. This fits the third case. M is even, the power of tangent is even, and N is odd, the power of secant is odd. And that's really the most difficult case here because it's one that we can't do with an identity and then a substitution. In this one, we use that identity that we used, tangent squared x equals secant squared x minus 1, to write as powers of secant only, then use the reduction formula for those powers of secant. So that fit that very last case. And every one of these should fit one of these cases. Let's try one that fits the second case. It's not going to be probably as difficult as the last one we just did, but I don't think we've seen any like that. We have seen some with the first case. So I'm going to stop my share here. But if I do that, I better use my mouse on my computer. And we'll share here instead. So something like integral tangent cubed x secant cubed x dx. So notice back on that sheet, the cases we want to look at are if n is even. So if the power of secant is even, that's the easiest scenario. We're going to split off a secant squared. We're going to write everything else in terms of tangents. And then we're going to let u equal tangent x. This is the next easiest case. We're going to split off a secant and a tangent. So we're going to take one secant and one tangent and split them off, leaving me with a tangent squared, a secant squared, and then a secant x tangent x dx. And notice the reason we're choosing this is that sitting right here, we have the derivative of secant x. And so we've made a conscious choice right now that we're going to let u equal secant x, so that du is secant x tangent x dx. Now notice the other part of this from that worksheet from last time is that we need to now write everything in terms of secant. So I'm going to rewrite my tangent squared x as secant squared x minus 1 times secant squared x secant x tangent x dx. All of this is du, and secant squared x is u squared, secant squared is u squared. So this is actually kind of nice. I have u squared times u squared minus 1 du, or integral of u to the fourth minus u squared du. And then I can just go ahead and integrate those powers of u to the fifth over 5 minus u cubed over 3 plus c, and back to x's, secant to the fifth of x over 5 minus secant cubed x over 3 plus c.
Good morning.
Morning, Gabe. Okay. So one really long problem and one more sort of shortish problem. Only one page for that last one. Do you guys have any other questions?
Sorry I joined late. Could you like briefly sum up like the past, like what we went over real quick?
We did one really long example, and it's written in chat. You might not be able to see what it was, but if you check back to the whiteboard, you'll be able to see it in the recording. And then we did the example that you see on the screen right now.
So I've only missed one page.
Well, you've missed the page that's sitting there plus 2 more pages.
Okay. Could you
Because it
go
was
back to
2
those?
pages long. You should be able to. I'm not sure that I can go back to it right now.
Okay,
But
that's
you'll
fine.
definitely be able to go back in the recording.
Okay, perfect. Thanks.
You're welcome.
And you upload those right after class, right?
As soon as I can. Remember, I do have another class at noon, so it might not be immediate.
We're not your first important?
Well, also the video has to process.
Oh yeah, that's true. I'm just playing.
Okay, other questions? Okay, so I am going to give you guys a much shorter problem to deal with. Let's try this one. Integral of 1 over, let's see which one I want to do. Square root of 4 minus x squared dx. Okay, so if anybody's got their handy dandy formula sheet, you can see if you can find a formula that fits this. If not exactly, then almost. This is one that you should have hit right toward the end of Calc 1. And there were 2 other formulas that were similar to this one.
Are you talking about the ln?
Nope, it's not the ln. The ln formula that I think you're thinking of was this one, the integral 1 over u du.
Yeah.
Is natural log of u.
Right.
Yeah, that doesn't fit here because if I let u equal that entire denominator, then du is much messier than just a 1. So that.
Could you break it up into?
That's not going to work.
Could you break it up into integrals?
Oh, ouch. You pained me, Gabe. You pained me. let me just, so this one is a valid one, but it won't work here. So I'm just gonna put a little won't work here on that first one. Then the next thing you said, Gabe, was can I break that up? Remember, we can't do this. If you have 1 over two things added together, that's not 1 over the first thing plus 1 over the second thing. That's a big no-no, right? You can't add denominators in a fraction. So that's a big no. The other thing that you can't do is that if you have a square root of a sum or difference, you can't say the square root of the first thing plus or minus the square root of the second thing. That's also a big no-no. That is not a property of square roots. If you had this would be true. If you had it like an a plus b all squared, then you could say that that's equal to absolute value of a plus b. So the very last thing is the only maybe valid thing we could do here, but I don't see a perfect square there anyway.
Wait, could we use trig functions for this?
Oh, you're getting close. You're getting warm. Not trig functions, but inverse trig function.
Okay, yeah, because we can't we use like isn't it like is it sine maybe?
It is inverse sine.
Okay.
Now there's a little glitch in this, and the glitch is that the number that
4
is
has to be
there
1.
is a 4 instead of a 1.
Right.
But we're gonna put up 3 more general integral formulas for inverse trig functions today.
Okay, cool. So I got it.
So you find, yeah, you got there. So this is gonna relate to an inverse trig function. And we're gonna get to these formulas in sort of a little bit of a backward way. I'm gonna remind you of the derivative formulas first, and then that'll give us the integral formulas. So first one, if you guys remember, let's see, if I have y equals sine inverse of x, or arc sine x, you might have used that notation, that means that sine of y is equal to x, right? Just rewriting that. And now what we're going to do is we're going to differentiate both sides. We're using implicit differentiation. Remember, that meant we think of y as a function of x, and we say, okay, derivative of sine y is cosine y times the derivative of the inside, dy dx. Derivative of x with respect to x is 1. So now we have it, dy dx is just 1 over whatever the cosine of y is. Now, this is a perfectly legitimate way to write the answer, but we would like to write the answer in terms of x only. So in order to do that, what we're going to do is we're going to take that y and we're going to figure out what it looks like. But remember, we have this little picture back here. The sine of angle y equals x. So opposite over hypotenuse would be x over 1. And then my missing side would be square root of 1 minus x squared. And so the cosine of angle y is square root of 1 minus x squared. So we've got 1 over square root 1 minus x squared. And we're almost to what we wanted. What we really wanted, though, was to have a different number there, like the 4 that I have. So in order to see how this might work, what I'm going to do is I'm going to just modify my little problem here with my derivative a tiny bit. I'm going to do so in blue. Excuse me. We're going to make that y equals sine inverse x over a, where a is any positive number. So a can be anything greater than 0. Now my picture changes that 1 to an a. It changes this 1 to an a squared. This would be an x over a. And this would be a 1 over a. So see how those a's just keep floating through the problem? And dy dx is 1 over a times cosine y. 1 over a. And cosine y is a squared minus x squared.
You just
A.
I got a question real quick.
Shoot.
So for the third step down, you have the y equals, and then you have the sine y, and then you on the left, and then you have the cosine y dy dx. You just multiply
That one, that
you
step.
multiply that by cosine inverse, right? On each side.
I did not. I took the derivative.
No. I'm talking about for the third to fourth step.
The third to fourth step. I divided by the cosine.
Oh, you divided by cosine?
I divided by cosine. I'm trying to solve for dy dx. It's multiplied
Okay.
by cosine, so
Yeah.
I divided by it.
Could you also you couldn't okay, never mind. I don't think you could multiply by cosine inverse because
No, because cosine inverse of y times cosine of y does not mean 1. Remember, cosine inverse of cosine of y would be 1, but then I'd have to be taking the cosine inverse of the whole side, and I would have really a big mess.
Right. Okay.
My goal is to get that dy dx by itself. It is multiplied by cosine y. The reverse operation for multiplication is division, so I'm going to divide by cosine y. Now, that last step might seem a little bit cheaty, so I'm actually going to erase that last step and show it to you in full, okay? So I have 1 over a times the cosine of y, but going back to my picture, cosine of y is square root a squared minus x squared over a. So there's another way to write it. And the a's nicely cancel, and I get 1 over square root of a squared minus x squared. So the derivative of sine inverse x over a, so if y equals sine inverse x over a, dy dx is 1 over square root x squared minus a squared. A squared minus x squared. Erg, a squared minus x squared.
That says G.
That says the opposite as well. That says the integral of 1 over a squared minus x squared in a square root is sine inverse x over a.
That is a y, right?
So this is my integral formula. What did you say, Gabe?
I said sorry, I don't know why I thought it would be a G, but it's a y. It says if y equals sine inverse of x over a.
That is a y. That is just a messy looking little y. I have no place for a G in here. You are
right.
correct.
I just wanted to double check. Thank you.
Okay. Merrick, I put it up in e-learning. I didn't send it in an email, but I did pop it up into e-learning. So it's there for you. You're welcome. Actually, this is it. Yeah, this one's in e-learning. All right, so now we still haven't done the problem we started with, but now we have a way to do it. So here's our problem, and we just need to identify what's the a value we're looking at.
4.
Nope. You're on the right track.
4 minus
I
x
would
squared.
say a squared is 4.
2.
So a is 2.
And how do we get a again? Can you just re-explain that for a second?
Okay, compare our original problem to our formula we just came up with.
So we just plugged it 4 in for, or you select a squared in for 4. Okay.
A squared is 4. So
Mhm.
A is 2, and that means that our integral is equal to sine inverse x over A, x over 2 plus C.
Why couldn't we just plug a in for 4? Or 4 in for, or yeah, a in for 4.
Okay, look at the formula again. The formula doesn't have a plain A in it on the left-hand side. It has an A squared in it. So you need to recognize where you're matching things up. We have a 4 right here. We
Right.
have an A squared right here. We don't have a plain A in our formula. We have an A squared on the left side of our formula.
Right. I was
So
talking
A
about at the beginning.
squared is equal to 4, which means A is equal to 2.
Right. I was talking at the beginning. Why we didn't use a equals 4?
Because that's not the form that I have.
Oh, okay.
Okay, so think about what I did in the beginning. I came up with this formula for sine inverse x over A using derivatives, but then in the end I ended up with an A squared. So
Right.
that is the A squared related to the original A, but that means that this number back here is the squared value.
And because we found that by using Pythag, right?
Yes,
Okay. All right. Thank you. That's why I was just curious about that. But okay.
that is right. Okay, so now we have a formula for integrating that leads us to an inverse sine function. We could do a similar development, and I don't want to spend the time doing each of these separately like we just did this one, but we could do a similar development and get formulas that lead us to inverse tangent and inverse secant. So I'm just going to show you guys those. So we've got this one so far,
Hey, can you go back
integral.
1 second?
In a minute, Gabe.
All right. Perfect.
So there's our integral formula that leads to inverse sine. Here's the one that leads to inverse tangent. And here's the one that leads to inverse secant. So take a look at those for a minute. And Gabe, I will go back to that previous page in just a minute, but I want to make sure everybody gets those 3 written down.
Perfect. No problem. I only have like 2 things to write down anyway, so it's not like
Okay, but please go ahead and take a look at this for a minute before I go back.
Perfect.
Okay, so I was just double checking something. And we actually need absolute value bars there. Okay, so let's peek back, and there's that previous page, Gabe. So, and actually, Merrick, though, those three formulas that I just put on that other sheet are not on the handout. What's on the handout are the problems.
We're
Okay,
good.
all
Thank
right,
you.
okay. And Merrick, are you good too? You found that handout?
Will you share that again if you don't mind? Or is it in
Share what
e-learning?
again, Gabe?
The handout? Or is it from
I actually didn't put it in here yet. I
Oh.
put it up in e-learning.
Okay, perfect. Thank you. I'm sorry, I just didn't know.
That's okay. And I can actually put it here. Let me see if I can load
Put
it.
e-learning if that's easier.
Well, I'm going to put it here and then it will be both places. Okay, so the problem we just did was my number one, almost. My number one was actually this. It was integral from 0 to 1 dx over square root of 4 minus x squared. But if we use that formula we just came up with, so we know that that's sine inverse x over 2. I'm not going to repeat that work because we just did it. And then we have to evaluate that from 0 to 1. So I want to do this to remind you of inverse trig functions and what it means to evaluate. So sine inverse 1/2 minus sine inverse 0. Remember, this means find the angle whose sine is. And your results should always be reported in radians, not in degrees. So sine inverse 1/2 is pi over 6. Sine inverse 0 is 0. Your calculators, depending on which calculator you have, will give the answer in approximate or exact form. Mathematica will give the answer in exact form, so you can always go back there and do it that way. So this one would be pi over 6. Okay, so now I want you guys to try one, and this is going to look a little bit different. Actually, I think we'll do this one together, then I'll have you guys try one with one of the other formulas. So this was number 1 on that worksheet. This is number 2. It's actually going to use the same formula, but we have to adjust a little bit, you'll see. Dx over square root of 1 minus 9x squared. So the problem with this one, is that we have this extra factor of 9 sort of floating around in here. And what we're going to try to do is make this problem look like the last one by making a little substitution. In other words, if right here I had just a plain u squared, then I'd be in good shape and I could apply my formula directly. So I'm going to go ahead and do that. This is substitution, but it's just got a little bit of a tweak to it in that we're not going to identify u initially. We're going to identify u squared initially. So we're going to say, okay, let's let u squared equal 9x squared. But that means u equals 3x. In other words, we're thinking of what's inside that square root as square root of 1 squared minus the quantity 3x squared, because it's the entire 3x that's getting squared. And then du equals 3 dx. So dx is du over 3. And we can put all of these things into place. Dx is du over 3. And now I have a square root of 1 minus u squared. or 1/3 integral 1 over square root 1 minus u squared du. Once I get to this form, I'm ready and good to go with using that formula. And so that formula said the integral is sine inverse u over a, but what's the a value? Well, a squared is 1, so a is 1. Or 1/3 sine inverse 3x. And my 3 looks a little funky, so I'll fix it. 3x, there we go. So notice on that one how I had to make a little substitution to make the formula fit. And this happens from time to time. All right, so take a peek at number 3. I want you guys to try this one on your own. This one's integral from 0 to 4 dx over x squared plus 9. Which formula fits on this one? So think about which formula fits on this. I'm going to go get myself a new cup of tea. Mine is cold. And let you guys think about that one. It's not the same formula that we've been using, but it is one of those 3 formulas that I gave you. So see if you can sort it out, noting what a is, and then evaluate the integral. Okay, give me a done in the chat when you think you have the answer to this one.
Would it be in degrees or radians?
So the true definition of the inverse trig function should be in radians always. So you could leave this in exact form. So for example, when we write this out, it's 1/3 tangent inverse 4/3 minus 1/3 tangent inverse 0. But tangent inverse 0 is 0. So our answer in exact form is 1/3 tangent inverse 4/3. So if they asked for exact form, you leave it just like that. If they ask for an approximation, you approximate in radians.
Thank you.
You're welcome. All right, let's try, let's see. Looking at the next one, but I'm actually going to jump down. Let's try number 6. So I'm going to skip over 4 and 5. 4 looks like 3 with a substitution. 6 looks like 5 with a little substitution. So let's try number 6, which is integral dx over x square root 4x squared minus 1. And this problem looks like our inverse secant formula. The difference is that instead of having just an x squared or a u squared underneath that square root, I've got a 4x squared. So I'm going to substitute again, like I did back on problem, which one was it? Number 2. So this is number 6 on the worksheet. I'm going to actually define that way. And I'm going to say, okay, well, it looks like u squared is 4x squared. So u equals what? Equals 2x? Right, Merrick. And that means du is 2 dx. Our a squared is 1. So a is 1. That's kind of nice. I'm going to put in all my substitutions. And I'm going to have to be a little bit careful here. Dx is du over 2. Du over 2. And x is u over 2. So notice that this is one of those problems where you could actually have forgotten to do the substitution and you get away with it, although that doesn't happen very often, so be really careful. Notice that those two 2's cancel each other out, and I end up with integral du over u times square root u squared minus 1. So this is 1 over a. I'm going to write 1 over 1 for emphasis, times secant inverse absolute value u over a, u over 1 plus c, or just secant inverse (2x) plus c. So nothing too horrid here. But I'm going to take a quick break from there.
Is that absolute value bars?
It is, and because those absolute value bars are built into that formula. And you can go back and read the results on that on why those absolute value bars come into play. They only come into play in the secant inverse formula. But essentially it's so that you end up with what would be quadrant 1 or quadrant 4 angle. You can
I'll
think
take
of it
aim at
that
this.
way, because that actually a quadrant 1 angle, because the secant inverse leads to a quadrant 1 or 2 angle, and the absolute value ensures that you're in quadrant 1. Okay, so I am going to switch my share, and I'm going to switch the share to that worksheet by this one. Okay, so I just want to sort of scan through these other problems and sort of show you where we're headed with this. So this next problem, number 7, looks sort of like maybe an inverse sine problem, but the square root isn't in the denominator like we expect for that formula. So that's a little bit problematic. Number 8 looks maybe a little bit like the inverse secant problem, but there's an extra factor of x on the outside. So that's a little bit problematic. Number 9, again, looks like the inverse sine problem, but there's this weird 3/2 power, so that's strange. Number 10 maybe looks like which one? Which one does that look like the most? Well, I don't like the square root, but other than that, it could look like an inverse. Where was the sum of squares? Was that in the inverse tangent or secant or sine? What do you think? Which one had a sum of squares in it? In those last few. Nope, not sine, Merrick. Sine was a squared minus x squared. So actually, let's do this. I'm going to stop that share and go back over here and share again. No. Erg. I want the whiteboard. Hopefully I can get back there. No. Oh yeah, there they are. Okay, they're going away on me. I'm going to write those formulas up here one more time. So we had integral 1 over square root a squared minus x squared. And that was inverse sine. And we had 1 over a squared plus x squared. And that was 1 over a times inverse tangent. And then we had 1 over x square root of x squared minus a squared. And that was 1 over a times secant inverse x over a. So which one of those has the sum of squares in it? Which trig function? It is tangent. Tangent. So what we're really going to do on that worksheet is when we see, we're going to use these formulas to lead us to what we're going to call a trig substitution. So in other words, we're not going to use these formulas directly, but we're sort of indirectly going to go back and figure out which scenario they fit. When we see each of these expressions inside here, so I'm going to circle them. When we see these guys, we're going to make a specific substitution. So when we see an a squared minus x squared, or even, we might even want to call it a squared minus u squared. We're going to let u equal a times the sine of theta. Okay. So we'll see how this works in practice in just a minute. But since this leads to an inverse sine, we're going to try this substitution where we let u equal a times the sine of theta. We're going to change everything into an integral involving theta. We're going to go back and use whatever method necessary. It might be something from the trig integral section. It might be something involving integration by parts. It might just be a basic substitution. But we're going to go ahead and integrate involving theta, and then we'll switch everything back to x's or u's or whatever we had to start with. When we see a squared plus u squared, we're going to let u equal a tangent theta. And when we see u squared minus a squared, we're going to let u equal a secant theta. Be really careful with the distinction between sine and secant. Notice that the order of the subtraction is important. So a is always a constant, and the u or the x is always our variable. So if you see 4 minus x squared, that's the sine category. If you see x squared minus 4 instead, that's going to be our secant category. So you have to be very careful about paying attention to the order of subtraction if there's subtraction in your problem. All right, so we are going to go now and try that problem 7 from that worksheet. And problem 7 was this one. I'm going to just do a new sheet. Problem 7 was integral from -2 to 2. So we'll have to evaluate this when we get done. Square root of 4 minus x squared. So our substitution is going to be to get rid of the x and replace it with a trig function of theta. And we're going to figure out the function by noting the order of subtraction. So this form is the a squared minus x squared form, where the a value is 2 and the x that's being squared there is just plain x. So we're going to let x equal a 2 times the sine of theta. So first things first, if you can get this far on a problem, this is really most of it, as long as you don't mess things up in terms of derivatives and integrals and a little bit of trigonometry. Now, we have two options on this. We could substitute this expression in just as it is and grunge through the trigonometry within the integral. I would much rather sort of do that work off to the side so that our integral stays a little bit cleaner. So that's going to be my choice. You can do things a little differently if you want, but we're going to draw a little picture off to the side to show ourselves what's going on here. So
Is that 2 squared minus x squared?
it is, because 4 is 2 squared. So 2 is identifying the a value.
Thank you.
Notice that this means sine theta equals x over 2. Remember you asked that question about the Pythagorean theorem earlier, Gabe?
Yeah.
We're going to use it again.
All right.
So I'm going to draw my angle theta. And again, my personal preference, I like to put it down to the left-hand side of the triangle. If you put it up at the top, it doesn't really matter, as long as you label your triangle consistently. So sine of theta is x over 2, opposite over hypotenuse. And the missing side is that square root of 4 minus x squared. Now our goal is going to be to turn everything in our integral into expressions involving theta instead of x. And there are two things in our integral essentially. There's the square root, and then there's the dx. We can't forget about either of them. They're both, one is just as important as the other. So I'm going to start with my dx because it's probably the easiest to forget about. Dx is 2 cosine theta d theta. You guys with me on that?
Yeah.
All
Yeah.
right. The other piece of this is the square root of 4 minus x squared, and I'm going to go back to my triangle for this. Notice this is the adjacent side to the angle. Which trig function used the adjacent instead of the opposite? Adjacent and hypotenuse.
Cosine.
Cosine. So I could say cosine theta is square root 4 minus x squared over 2. Which means square root 4 minus x squared is equal to 2 cosine theta. I'm going to leave my limits off for a minute. All right, square root of 4 minus x squared is 2 cosine theta. Dx is another 2 cosine theta d theta. And that means that I am integrating 4 times the integral of cosine squared theta d theta. And if I were to put limits of integration on this, I should switch them from limits of x for x to limits of theta.
Do that.
What'd you say, Gabe?
Can we do that?
Can we do what?
Or we're gonna have to switch it to limits of.
Okay, sure.
We do have to, right? Or no?
Well, I mean, you could go back to limits on x, but I like to go ahead and switch, so let's do that.
All right.
When x is 2, 2 equals 2 sine of theta. So sine theta equals 1. And remember, we're dealing in radians, so theta is pi over 2, 90 degrees. And my upper limit becomes pi over 2. When x is -2, -2 equals 2 sine theta. Sine theta is -1. And remember, we do need to inverse sine, so it would be 3 pi over 2 or negative pi over 2 is really what we want. So that we're working with our inverse sine function.
Can we use -3 pi halves?
-3 pi halves? No, that would be the
3
same
pi
as pi over 2.
I mean 3 pi halves.
Probably possibly gonna lead us to some troubles. So you should really stick with the range for the inverse sine function, which is from negative pi over 2 to pi over 2.
But I'd still get the right answer if I were to use 3 pi halves if I did the integral right?
You could, in some cases, end up with a quadrant problem. I don't think you would here, but it would be probably poor form. I would stick with really the answer to this. And here's the key, Gabe. In this problem, when I went to here, it's because I went theta is sine inverse of -1. And sine inverse of -1 is not 3 pi over 2. It is negative pi over 2. Because the range of the sine inverse function is values of the angle that range from negative pi over 2 to positive pi over 2.
Okay, thank you.
You're welcome. All right, so now we've got to integrate this trig function. We've got a power of 2, and that was our half angle formula, where we rewrote that as, let's see, what was it? Cosine squared theta is 1 plus the cosine of 2 theta divided by 2. So that was one of those identities that we had last time for dealing with even powers of sine and cosine. I'm going to pull out my constant, my 2 now, because 2 goes into 4 twice. And I'm integrating from negative pi over 2 to pi over 2, 1 plus cosine 2 theta. Now, this is where you want to be really careful. Remember, our angle is theta. So what's the integral of 1? Our variable is theta. Integral of 1 is theta, not x.
Wait, you said integral. Oh, yeah. Okay.
Our integral of 1 is whatever our variable of integration is, but our variable of integration is theta, so be very careful. Integral of cosine 2 theta is sine 2 theta divided by 2. And we're evaluating this from negative pi over 2 to pi over 2. So I've got 2 times pi over 2 plus sine of negative pi over 2, positive pi over 2, minus negative pi over 2 plus the sine of, this time, negative pi over 2. But nicely, the sign of any multiple of pi is 0. So this term's 0, this term is 0. Close my parenthesis.
Is that, you said that trick you said?
What trick?
That any multiple of something.
Well, it's not really a trick, right?
I guess I didn't hear it.
The sine function is periodic, right? And the sign of any multiple of pi is 0.
Yeah.
Okay, I don't think it's a trick.
No, it's not. I just didn't want to make sure I missed the easy trick, but it wasn't. Okay.
Okay, so what's left? 2 times pi over 2 minus negative pi over 2, but that's just pi. So 2 pi. Okay, so think about what's going on this. We're starting with an integral that doesn't fit any of our basic formulas. We're making a substitution to give us trig functions instead of algebraic functions. Then we're integrating, and then if this had been an indefinite integral, we would have written our final answer in terms of x. Since it was a definite integral, we were able to evaluate it by plugging in. So let's try another one. I think, Yeah, we'll go ahead and we'll do that was number 7 on this sheet. So I'm gonna label it as.
Did you mean to write 0 squared at the bottom right?
I was just saying that there was a 2 in that denominator, Gabe.
Yep.
And I was just saying that whole thing was equal to 0, right? Because sine of negative pi is 0. So that term and that term were both zeros.
You weren't saying the denominator, you were saying the whole term,
The
right?
whole term was 0. No, the denominator was 2. The denominator definitely wasn't 0, right? All right, we are going to try this next one. We'll probably have time for like 2 more maybe. Integral of dx over x squared times the square root of 4x squared minus 9. So the first thing we want to think here is, which one of those formulas does this fit? So I'm going to pop myself back to a previous page, this one. In my square root, or in my expression, which do I see? Do I see the expression that leads to sine, tangent, or secant?
Can you ask the question again? I didn't hear the
Do I see the expression in here that deals with sine, tangent, or secant?
I guess I didn't see the problem.
Okay, so let's go back to the problem again. So now, do you have those formulas back somewhere in your brain?
Yeah, I haven't written down.
Okay, so
You
let's
just
go,
write those, right?
let's go back to the problem, which seems to have disappeared from my consciousness. Let's go back to the problem, which was this one, dx over x squared square root 4x squared minus 9.
Secant, inverse.
Secant, okay. So normally this would lead to a secant inverse, and if we just had a plain x there, we could use the formula. But we don't, so we're going to use the substitution. Now, I have to recognize what's being squared. So in other words, this is the expression that I see. A u squared minus a squared kind of expression. And the u squared is 4x squared, the a squared is 9. So tell me what u equals. Be really careful. Try not to blurt until you think about it. If
2x minus 3.
Say that again.
2x minus 3.
Okay, be careful. That does not say 2x minus 3. I think what you're saying is 2x squared minus 3 squared. Is that what you meant?
Yeah. That's exactly what I meant.
Okay, so u equals 2x and the a value is 3. And the substitution we were going to make was to let u equal a times the secant of theta. So we're going to be really careful with this. 2 times x equals 3 times the secant of theta. Not plain x, but 2 times x. Why do we need 2 times x? Because when we square it, we get that 4x squared. If we used a plain old x, we wouldn't get the 4x squared in our integral. We would get a plain x squared. Okay, so messy time now. Let's draw the triangle. I'm going to solve for my trig function. Secant theta is 2x divided by 3. And which ratio is secant? It's 1 over cosine. So it's hypotenuse over adjacent, right? And my missing side, Pythagorean theorem, is square root 4x squared minus 9. And it should not be surprising to you that the expression you see on that missing side is the expression we were working with in the integral. It should be. So now let's see if we can get all of these little pieces put together. I've got u is right there. 2x is 3 secant theta. Let's see. So we know what 2x over 3 is equal to. I'm going to go back and look at my integral. It's got an x squared in it that I'm going to have to deal with. It's got this square root that I'm going to have to deal with, and it's got the dx. So, let's start by solving this thing for x. X is 3/2 secant theta. That means we should be able to plug in for our x squared. We should be good there. And we should be able to get our dx. Dx is 3/2. Derivative of secant is secant tangent. So I'm going back here and I'm looking, I've got my dx, I've got my x, so I can plug in and get my x squared. And then this square root, again, some students like to just grunge it out. I think it's a little simpler if we go back to our picture in our triangle and notice that tangent theta is square root 4x squared minus 9 over 3. So that means that 3 tangent theta is square root 4x squared minus 9. So there's lots of pieces coming together here. We're doing some algebra, we're doing some trig, we're using some identities, and then we're going to go back to our integral, shove everything in, cancel what we can, and hopefully we come up with an integral that's not horrible, or that is at least doable. So while this looks a little messy, it's really a matter of keeping track of everything. 3/2 secant theta tangent theta d theta. That's my dx. X squared is 3/2 secant theta squared. So 9/4 secant squared theta. And my square root is equal to 3 tangent theta. So take a peek at that. Make sure you can see where all the pieces came from. It's a little bit messy. But the first thing I notice is that a lot of the messiness is just constants. I've got a 3/2, a 9/4, and a 3 that are all constants that I can factor out to the outside. And then I've got some secants and tangents, and some of those are actually going to cancel, right? So let's see. I am going to take all of those constants and pull them out to the outside. I've got a 3/2 on the top and a 9/4 times 3, so a 27/4 in the denominator. And then I've got a secant that cancels with one of these secants, and a tangent that cancels with a tangent. So all that's left in there is a 1 over secant theta d theta. Okay, so all of you guys with your trig identities, 1 over secant theta is which trig function?
Cosine.
Cosine. So this is integral of cosine theta d theta. We should invert and multiply there, right? So it's 3/2 times 4/27. 3/2 times 4/27. And that looks like 2/9. Integral of cosine is? This isn't a trick question. This really ended up pretty nice, right? Integral of cosine is sine. We've done the calculus. Now, we do have to go back and write our answer in terms of x. But remember that triangle that we spent so much time on earlier? Drawing a neat triangle and labeling all the sides? Can you go over to that triangle and tell me what the sine of theta is?
4x squared minus 9. The square root of 4x squared minus 9 over 2x.
Square root of 4x squared minus 9 over 2x. You are correct.
For the sine of theta, yes.
And there's our integral, all written in terms of x. We could actually cancel those 2's and clean that up a little bit. So our final answer I would write as square root 4x squared minus 9 over 9. Oh, what did I just, no! I know what, over 9x. I was getting close to the little trash it button at the bottom corner of my screen, and I trashed that.
Oh my gosh, I would have been so upset.
Undo worked, thank goodness. That would have been sad. Okay, so there we are. Square root of 4x squared minus 9 over 9x plus c. And a check should reveal that that's correct. Or looking into Mathematica should reveal that that's correct. Or doing that on your calculator should reveal that that's correct, depending on which calculator you have. And which problem was that one? That was number, let me see. That was number 8. That worksheet. Okay, so we are going to take a peek at 9, 10, 11, and 12. And what I want to do with those right now is I just want to have you guys give me the substitution that you would use. So we started this last problem by letting x equal, or 2x equal 3 secant of theta. So on number 9, I want you to think about what you would let x or something equal. So what would your substitution be? And when I say that, I mean, what would your specific substitution be? So you need to say the whole thing, like let x equal 7 sine of theta, or let x equal 3 tangent of theta, or whatever it's going to be. So see if you can identify for 9, 10, 11, and 12, what substitution you should make. We'll record again. Okay, so which trig function do you guys think for number 9, and which constant?
Sine.
Sine?
Am I wrong?
You are right. What's my coefficient?
1.
1. So we're going to let x equal sine of theta. What about number 10? Looks like the coefficient is 1 again. And the trig function is?
Cosine.
Nope.
Tangent.
Tangent. Remember, in our 3 choices, cosine was not in there. It's sine or tangent or secant. That's it. You will never use the co-functions on these trig substitutions. Sine, tangent, or secant. Tangent. It's tangent theta because this is a sum of squares. 11 is the same expression. It's just squared instead of square rooted. So it's the same substitution.
Wouldn't it be tangent inverse and sine inverse, or no?
Absolutely not.
Okay.
just go back to that last problem we did. We are not going to substitute the inverse trig functions. These often lead to them, but our substitution is the trig function itself, not the inverse trig function. It's the trig function itself that leads us to this sort of nice trig integral as opposed to a messy algebraic integral. I guess that's sort of the plan, to lead ourselves from an algebraic integral that's very messy to a trig integral that, while it might be kind of long, at least it's doable. And finally, that last one. Also a tangent,
No, I'm not sine. Sorry. Yeah, tangent. Yeah.
but with a coefficient of
3.
3. So 3 tangent theta. Okay, Aaron C. I'm going to let you pick. So Aaron C., you get to pick which one of those you want me to do, 9, 10, 11, or 12. We don't have time for all 4 of them. So we have 9 minutes. Number 10, okay. So 10 is the one with that ugly square root and then the x cubed in the numerator. Okay, we'll do number 10. So integral x cubed over square root x squared plus 1. And this was from 0 to 1. Okay, and we said we were going to let x equal tangent theta. So I'm going to draw my triangle to start. Tangent theta is x, so x over 1. And there's my square root of x squared plus 1. So that's kind of nice. And let's see, we know dx is secant squared theta d theta. And that square root coming over here to my triangle is the secant function. And the fact that that was a 1 for our constant makes this extra nice because we don't have messy constants to deal with. So let's see if we can get all the pieces together, and we'll have to change limits again. So x cubed is tangent cubed theta. That's maybe a little bit ugly. Square root of x squared plus 1 is secant theta. And dx is secant squared theta d theta. So if we take a look at that, it's really not maybe all that bad. Notice a secant cancels. And so we are integrating tangent cubed theta, secant theta d theta. And our limits, they were 0 to 1 for x. So let's change them to limits for theta. If tan theta is 0, theta is 0. And if tan theta is 1, that's 45 degrees. So theta is pi over 4. So we've got new limits. And now this is a matter, and this is probably why this section maybe gives students troubles. This is a place where we have to go back and use those ideas from the trig functions. So let's see, I think this is one where, notice if we split off a tangent and a secant, we should be able to write everything else in terms of a secant, so we'll be good. So I'm going to split off a secant theta tangent theta. And then I'm going to write everything else in terms of secant theta. So I've got 0 to pi over 4. I've got a tangent squared theta, which we're going to change. And then I've got a secant theta tangent theta. And I'm going to change that into secant squared theta minus 1. And so finally, notice we get a U substitution. So we got lots of things in here. We're using the ideas from trig functions. We're using a basic substitution now. We're going to let U equal secant theta, so that du is secant theta tangent theta d theta. And I'm going to fix my equal sign because it got kind of funky there. And I've got integral u squared minus 1 du. I didn't switch limits to u values yet, but I can do that. U cubed over 3 minus u, evaluated from wherever to wherever. Let's see, theta was pi over 4. So secant of pi over 4 is root 2. And theta equals 0. Secant of 0 is 1. So I'm evaluating this from 1 to square root of 2. So I've got root 2 cubed over 3 minus the square root of 2 minus 1/3 minus 1. So a little bit of algebra to mess with there, but you should be able to do that. You can convince yourself that it's this 2/3 minus 2 root 2 over 3. Something's wrong. 2 root 2. No, I think it's just minus root 2 over 3. Yeah, because this would be times 3 over 3. And this would be 2 root 2. So minus, yeah, that should be it. You can double check me, but I think I got that right.
So is your answer at the very bottom wrong?
No, my answer at the bottom is right. That's just simplified. What I circled is simplified. I didn't want to go to a new page where you wouldn't be able to see this anymore. So if I take root 2 cubed and divide by 3 and then subtract square root of 2, which is the same as 3 root 2 over 3, and then subtract the quantity 1/3 minus 1, I will get what I have inside the circle. Now, keep in mind, if you wanted to, you could back yourself up to theta values or to x values, if you even wanted to go all the way back to x's, but you don't have to. In this case, since this was a definite integral, it's usually simpler to just go ahead and switch values so you don't have to get those messy expressions involving x in there. If you did, then, you know, if it wasn't a definite integral, we would have to do that. We would have to write our final answer in terms of x, and we certainly could. So I am going to leave us at that because that has us at 11:54.
I thought you were saying something earlier. I thought you were saying at the thing at the very bottom of the page and the bottom right was the answer. That's why I was asking. I thought you were saying
Well,
that.
it's not incorrect. It's just not simplified, right?
No. I thought you were just saying 1 over 3 minus 1 was the answer.
No, that is not the answer. That remember
I
when
didn't see
we,
the minus sign.
okay, do you see what I did there though? I was evaluating.
Yeah, I see.
Okay.
Yeah, I see. Yep.
Okay, good.
Yep.
All right, so I'm going to let you guys go. Remember, no class on Wednesday because I'm at a conference. Virtually, I will be around. You can send me questions via email, or you can post questions in e-learning. If you post them there, that would be nice for everyone to see results or answers to those questions, because quite honestly, remember, you often have the same questions. Okay?
Okay, thank you.
You're welcome. Have a good week.
Thank you, you too. Bye-bye.
Okay,
You too.
bye.
Bye. See you next Monday.
Have a good week, everyone.